Who can explain it from the start? Sakatoa, yeah. Alberto? Trig ratios, sin, cos, and tan, can you explain them? Yeah.
Let me understand this we use sine.
It's what?
Like doing the hypotenuse.
Yeah.
And the after the
Okay, so we kind of have, we know some stuff because we've learned it off. Sine of an angle, let's call them all theta, is something called the opposite over the hypotenuse. Cos of an angle, so theta is a Greek symbol that we use a lot for angles for no particular reason, sometimes just use A and B. The cos of an angle is the adjacent, which is short, over hypotenuse, and the tan of an angle is equal to the opposite. Yes. But that's all meaningless. Isn't it really? We don't have a clue what's going on still. It's from finding angles, but what's that about? How does this help us find an angle? Okay. Yes. Why do they work? Okay, no, you're on the right track. Okay, let's have a look at right. This works for right-angled triangles. All right. Let's have a third one. Oh, too big. There's just three. You don't need to take it at the moment. Take it down to your nuts. All right. I'm looking specifically at this angle here in the corner. All three. Focus. All three are right angle triangles. 1, 2, 3. Alberto.
Oh yeah.
Okay, all right, okay. We're getting straight into the theory. We're saying the one that's called opposite. I know that, yeah. Okay, so we know that this is opposite, isn't it? Because it's opposite the angle. This is adjacent because it's alongside the angle. And this one over here is the hypotenuse. Well, we knew that from Pythagoras anyway. But what I'm talking about, what's it called when we put it like that? That's a fraction, isn't it? A fraction is a ratio as well. Yeah, put them over. Okay. Let's call these. There's no numbers yet. I'm just going to call this triangle A, B, and C for when I'm talking about each triangle. Which has the largest angle marked? As in, I've marked these three angles. Which is the largest angle, do we think? You visualize. There's not C anyway. It's probably B, because this side is a bit shorter. And this side is very long, and that kind of creates that long. Whereas this one, it's probably around 45 degrees, because that length is kind of the same as that length. I'm reckoning about 45. This is quite small, because this length here is short, and this is a very long length. Okay, so what have I compared each time there? I've compared this side to this side, this side to this side, this side to this side. What's this side called again? Opposite. It's opposite the angle. Okay, I'll finally write opposite. This is the adjacent. So I've compared opposite and adjacent in all triangles. So what have I really compared? From which one of these? Tan. Opposite and adjacent deals with tan. Yeah. So I've looked at the ratio of opposite to adjacent in each case. I've looked at the ratio. Here it's about 1 to 1. Yeah. The opposite and the adjacent kind of level pegging. Here in the second triangle, the opposite wins, doesn't it? It's way bigger, and the adjacent is small. So the opposite is winning. If the opposite is winning, we can see it's a larger angle. If the adjacent is winning, the ratio versus the opposite, it's a smaller angle. Does this always work? If we have a long adjacent and the opposite is small, will it always be a small angle? Is it ever possible to have a small opposite and a large adjacent, but have a large angle here? No, it's never possible. So what they do is they use this fact that we can look at the ratios. If the opposite is tiny and the adjacent is huge, this is a sliver. I can't even draw it, it's so small. That the angle is so small. But it goes from so small to, if I could draw the next one up and have a tiny adjacent and a huge opposite, we're getting closer and closer to 90 degrees here with this angle down here. Yeah, that angle there is getting closer and closer to 90 degrees. It'll never reach 90 degrees, will it? It won't be a triangle anymore if it does, because this one's 90 and this one's 90. So what they do is they use those ratios to find the sizes of angles. And if we're given the opposite and adjacent, we know how big the angle is. So for instance, without even drawing it, if the opposite is 5 centimeters in length and the adjacent is 2 centimeters in length, so the opposite is 5 and the adjacent is 2. Picture that. Is it more than 45 degrees? Is it a big angle? If the opposite is 5 and the adjacent is 2, is it more than 45 degrees? No. So the opposite is 5 centimeters. 1, 2, 3, 4, 5. 1, 2 over. The angle down here, I think it's going to be more than 45. How do we know what 45 is? Because I'm using, if they're in perfect harmony, 1 to 1, what have I got? 1 to 1, if that's the same length and that's the same length, it's an isosceles triangle. And both these then would be 45 degrees. Now I want you to take, if you have a calculator, take out your calculator. Now we're going to start off tan. We're going to use tan. But type in tan 45 degrees, so you're getting the ratio. No, not tan, not there. Just normal tan. That would be standard. So, minus tan 45 degrees. I'm testing this one out. I've said that's 45 degrees, and I've said it because the opposite and adjacent are exactly the same length. What do I get? 1. So the ratio is 1. What does that mean? Well, if that's 3 and that's 3, what's the ratio? 3 over 3, which is 1. Now, if the opposite is winning, like in this case, 5 to 2, I expect that this angle is bigger than 45 degrees. And that's where tan inverse comes in. If I have the ratio, so I have, well, if I had 1, could I go back and find 45 degrees? I can. And that's where so I know tan 45, that's all you've done your calculator, equals 1. Just type it in. If I want to go backwards, the tan inverse button, so second function of shift tan, if I put in 1, don't put it in the box, what angle do I get out? 45. So I can, if I have the ratio, this is the ratio, so it's really 1 over 1, or 3 over 3. If I have the ratio, I can work back to get the angle. If I have the angle, I can get the ratio. So, what is my angle of this one? In other words, if I have the ratio, 5 over 2, and I want to find the angle. So do tan inverse, put that 5/2 in brackets so you're not going to get confused. I'll do it on mine. Maybe. This thing I don't have to use the arm calculator. What is it? 68 is yours in the 68. Yeah, it's more than 45 degrees. That was my 68.
So how do you do the negative?
There's a shift in the second function. Shift time. Shift time. 60, let's call it 68 degrees. Subset. Tan is working out for me. Now, give me a ratio, the opposite length and the adjacent length, that's definitely less than 45 degrees. Less than 45 degrees. Without using a calculator, just give it to me here. Look at this. It would be like this one, wouldn't it? That's definitely less than 45 degrees. 1/5? Let's try it. So what's the tan inverse if I know the opposite is length 1 and the adjacent is length 5? What is it, 18? 11 degrees. So this isn't just random numbers. And then just, when I get a number here, 1/5, often you get it as a decimal, it's like 0.2 here, but what does that mean? It's a ratio that just changed to a decimal. Because 1/5 is 0.2. It's how much bigger or smaller the opposite is than the adjacent for tan. And this works for all of them. If you're given the length of the hypotenuse and the opposite, you use sine. Let's look at that. Here's my makeshift. We make some triangles that help us with sine. All right, so we're going to look at, let's build another. That's the same one again. I don't know how I wrote it down. The one for 45 degrees. Okay, that's always a good place to start. Let's just look at this angle this time, just to be confusing. I'm going to take that one. Okay, I'm looking at hypotenuse and opposite now. So let's call that hypotenuse, opposite. I'm going to design some triangles that help me out. I'm going to try and get a hypotenuse the same length. So it's about the same length and tighten up the opposite. It has to be a right angle triangle. So the hypotenuse is about the same length, but the opposite is a bit shorter. I'm still looking at this angle up here. Let's get one with the opposite a lot longer and try to have the hypotenuse a similar length. So the opposite has to be longer. Hypotenuse needs to be, now this is difficult to draw. Hypotenuse is the same length. Oh, I have a problem. What's my problem? If I'm drawing the hypotenuse of a similar, I've drawn the opposite really long. In fact, a lot longer than the hypotenuse, right? The hypotenuse is about that. What? It's not. Good. The hypotenuse has to be the longest side, so I can't go any further than that. These two are almost the same length, but let's try and make it as long as I can do it. Okay. Shorten this down a little bit. That's my attempt to make a long. Okay. This kind of looks the same as that one. Pretty terrible. Try and. Oh, let me shorten that right down. Shorten that right down. You actually have to think about the adjacent length. That is the hypotenuse, and that's quite a long length as well. Okay, we're there. That's an angle. Okay, so this is the call this A, N, B, and C. The very first question, if I'm not comparing hypotenuse and opposite yet, I just want to know which is the biggest angle. A, B, or C? Which is the biggest angle? C. B, C, B, C, C. Which is the biggest angle? Well, it's either A or C, isn't it? A or C, depending. A It could be close. So I'm going to compare opposite hypotenuse. But we definitely think that B is smallest. Don't we? Because this is really tight. And if I shrink that in even more, the angle is going to get even smaller. So the smaller the opposite, even if the hypotenuse kind of stays the same, the angle is going to get smaller. So the bigger the opposite, the bigger the angle. Yeah? Okay, so let's put some figures on this. So our previous example with a isosceles triangle, let's just call this length 1, this length 1, I could have called it 3 and 3 again, but I know it's 45 degrees, because I did it in the last one. What's the length of the hypotenuse here? What particular theorem would find the length of the hypotenuse? Pythagoras, yeah. 1 squared plus 1 squared, square root. So 1 plus 1, square root, is square root of 2. So whatever the square root of 2 is, it's 1 point something. We just leave it as square root of 2. Okay? Alright. Alright, we go decimal. We want to go decimal. Going forward. Okay, so it's the biggest one. Right. The opposite is smaller than the hypotenuse here. Okay. What happens when I started making the opposite bigger than the hypotenuse? What happened when I tried to draw it? It couldn't happen. All right, try it on your calculator now. I want you to make the opposite. So we're going to look for sine of an angle. So that means we have to use sine inverse if we're dealing with the ratio. The opposite, let's call it 5. And the hypotenuse is 2. Let's make the opposite bigger than the hypotenuse. See what your calculator does. Let's see what does it do. It's not an error. It's your calculator is going to say error. It's going to say error. Yeah, you're giving me absolute rubbish. Yeah, this is not possible. Not possible. So you're not going to get ratios that are bigger than 1. Well, what happens? Okay, let's say there's what's the sine inverse of 1? Can we get the sine inverse of 1? What's the sine inverse of 1? 90? Sine inverse 1, yeah, sin inverse 1. 90 degrees. Does that make sense? It's a right angle. That means the opposite of the hypotenuse would have to be the exact same length. So if they're the same length, they must be really close together, in fact, 90 degrees. Top of each other almost. Must be that close. Okay. So make me a large angle. What would be a large angle length? What would be a large angle in this? I want this big possible angle. Give me a ratio. 6 and 9. 6 and 9. All right. Do sine inverse 6 divided by 9. What kind of angle is that to? 41.8. So about 42 degrees. All right. I won't figure it out. 6 over 9 is not big enough. Wait, 28. Wait, hold up. So by numbers. Oh, 28 over what? 28 over 30. I think. Not mine. Let's see. What's 28 over 30? 68. 68 degrees. All right. Well, let's do 29 over 30. I think if the hypotenuse stays the same length, but the opposite's got quite a bit bigger, not much, it should be into the 70s? 75. Okay, well, let's make this 29.9 over 30 sine inverse. Let's get us close to 99. Was it 85? 5. So we're getting closer and closer. You can see if I increase that until, well, once it's the same number with the same number, it's 1, and that'll be 90 degrees. So if I get closer and closer to a smaller, or larger fraction, should I say, closer and closer. That's the ratio. You can see the ratio at work there. The higher the opposite is, I can form that angle. It's getting larger. And that's the same for every single right angle triangle. And that's why all these work. Same things work where it is just the opposite. You're given 2 bits of information, you can find the angle based off of 2 bits because they are in a ratio. And that's the point. I mean, the fraction. The bigger the fraction in sine, the bigger the angle, and it's actually opposite in cos. The bigger the fraction in cos, the smaller the angle. All right. Time's done. Oh, time. All right, so I'm going to give you some easier questions on these and see how you get on. I'm not going to give you too many exam questions, just a few exam type questions on trig ratios. You should remember them from last year. I've recorded this so you can watch it again. And